Well, out of respect for everyone's time, I'm going to go ahead and get started. This will be recorded, so if you want to go back and reference it, feel free to do that. Um, I am super excited to be giving this workshop today. Um, my background is I'm a developer. I work for Quicken Loans, and my focus is mathematical planning. And that's what I get really passionate about. We also use the F# language, which I think is a wonderful language for doing this kind of work. And what I'm hoping to do with this workshop is just to expose people to these tools and what they enable us to do and the kind of problems that they're really useful for. I sincerely believe that if there was just more awareness of these tools, we would see a lot more adoption of it. But because it didn't come from the computer science departments, there's just not an awareness of it. And so what I'm hoping to do is to give back to the community and drive awareness and show like, hey, yes, mathematical planning, math stuff. There's very little, if any, mathematical notation in this entire workshop. It's all very practical, very easy, and try to keep it very approachable. And so I'm super excited to be doing this. Thank you for taking time out of your day to do this. This is actually my birthday. And I had the day off, and I'm like, you know what? I can't really think of anything much more fun than doing this. Giving a workshop and talk about my favorite subject using my favorite language. So I'm super, super excited to get into it. So let's go ahead and get started. Thank you so much for the happy birthdays. Let's switch over here. Mathematical planning with .NET. What is this workshop going to look like? The majority of it is going to be the introduction to mathematical planning. And it's going to start very simple, easy, maybe overly simplistic for some people. But don't worry, the difficulty will ramp up and the complexity will ramp up. So don't be put off by the first few models that we do. It'll get more interesting and more complex. We'll then have a section where we talk about the structure and testing of production models. There's some things that we have learned by doing this in production at scale, where if you just follow some pretty simple practices, it's going to make your life a lot better in terms of code maintainability and testability. And so we're going to go over an example project that is also included in the repo. It's a very simple model, but it kind of illustrates how to structure code and how to put it together in such a way that it's easy to grow and maintain and debug. And then we're going to have a discussion about different deployment scenarios. And this is a lot of best practices from software engineering. It's nothing shocking, but again, coming from having put some of these models into production and having supported them, there's different ways to deliver it, which can make your life easier or harder. And so we will have a discussion about some of those scenarios. And then at the end, there's a Q&A. And that Q&A is open-ended. This workshop is scheduled for 4 hours. The Q&A section is right now 15 minutes at the end. But if you have questions, my day is open-ended. So we will get your questions answered. I'll stay on for as long as I need to get people's questions answered and provide whatever information I can to make sure that you come away with the understanding that you feel that you need in order to be able to apply this where you work. Some of the details we need to go over before we jump in. We will be taking 10-minute breaks at the top of the hour. And I will kind of gauge that kind of where we are in the content. Like, okay, I might take it a little earlier, a little after the top of the hour, but we will be having breaks once an hour to let people get up, stretch their legs, go to the restroom, refill their coffee, whatever it is that you need. So don't be worried that this is just going to be like a wall of information coming at you. We are recording this. You may have noticed when you logged in that the meeting was already being recorded. When we're done with this workshop, I'm going to edit it down to just the content. So the Q&A portions and just the discussions we might have during the breaks, those will not be included in the recording. And the reason I'm doing that is I want people to feel free to kind of ask whatever question they want to and not worry about like, oh no, I'm going to look stupid or something and it's going to be on the internet forever. I've done stupid at scale. So I know what that feeling is like. So realize like, yes, the whole thing's being recorded right now, but only the content portions are going to be released for people to be able to view. So again, this kind of comes to the code. I'm going to be demonstrating a lot of code, writing a lot of code. You can follow along if you want, but don't feel like you need to, because there will be a recording. And I also provide solutions. So if you didn't catch something, you could always look at like, okay, well, what was the way that he actually solved this? So it's there for reference. I provided this link to the repo with where all the content is. Feel free to clone that, use it as you will. And like I said, I'm trying to provide a gentle introduction to this subject and to kind of ramp you into it. There's a lot of places you can go from here. I am working on follow-up workshops to go into more details, more complex modeling scenarios. So, but this is meant to like whet your appetite. Like, oh, this is really interesting and to be usable. The stuff that we come away from here with is sufficient to solve a lot of real world problems. So don't feel like, oh, I'm not going to get anything useful out of this. Like, oh yeah, you absolutely are. And with the stuff that we use here and we will learn here, it's sufficient for doing a lot of what we do at my work currently. Like I said, I'm at Quicken Loans, and so we're using mathematical planning to optimize trading of mortgage-backed securities and blah, blah, blah. That's only interesting if you're into that domain. So I won't go into it. But the stuff does scale, and it is very useful and applicable and has made Quicken Loans a significant amount of money. And that's about all I'm allowed to say about work. So let's get on to some content. I hope you're as excited as this guy, because this is how excited I am internally about this subject. So let's dive into it. Introduction to mathematical planning. And I'm going to switch over to this set of slides. So questions we are going to answer in this section. What is it? What is it? What is mathematical planning? Matthew, when you use this term, I have no idea what you're referring to. What is it good for? Like, when should you use it? And how do we do it? And that's a lot of what we're going to cover in this first section is like, how does one do mathematical planning and how does it relate to machine learning? Because this is one of the questions that I get quite a bit with people saying like, well, Matthew, you're talking about mathematical planning, but it kind of sounds like machine learning. And we're going to disambiguate that a little bit because machine learning is very cool, but it's really for a different set of questions than what we're concerned with here. Before I get into that, though, what I like to do is kind of anchor us with a why. Why do we care about these tools? Why do we care about this subject? And the example I give to people is this. And some of you, I'm going to date myself a little bit. Some of you may recognize this, may not. So this is New Orleans after Hurricane Katrina. And when I first started teaching this material as an adjunct professor, I would pose this question to the students as the opening question for the class, which is, you've been put in charge of the relief efforts in New Orleans after Hurricane Katrina. You have this much food, you have this many boats, you have this many volunteers, and this much medical supplies. Give me a plan that's going to save the most lives. Right? How many people do you put in the boats to go search for people? How many people do you put in the medical tents? How many people do you have cooking food and preparing things? That is the quintessential mathematical planning problem. And we really care about that answer because saving human lives is kind of important. And so, yeah, a lot of the time this tool gets used for other domains, but fundamentally this tool, mathematical planning, is a powerful way to be able to identify the best possible plan to save the most lives. It's a method for finding that best plan given a set of decisions to be made, like where do I put people, constraints that I need to obey. I only have so many supplies, I only have so many tents, I only have so many boats, and a quantifiable objective. In this case, save the most lives. That is how I measure success. And the other way I like to put it is it's the mathematics of caring for people. It's a way of choosing a plan that accomplishes the most good possible. And that is why I get so excited and so pumped about mathematical planning and want more people to use it. Who uses it, right? Which is a great question. What industries are actually taking advantage of mathematical planning? Well, one of the first industries to adopt the use of mathematical planning was actually the freight industry, moving goods around the world. It's a classic problem where I have this many goods at this location. I have these methods for transporting that material from two different locations. I want a plan that's going to move those goods in the most efficient way possible in a very cost-effective way as well. And my decisions are like, do I put this box on this train? Do I put it on this jet? Do I put it on a boat? So it's all those decisions involved in how do I move freight around in order to get it to its end location in the most efficient way possible. There's also the financial industry. And so this is where you find me, where you have questions about, hey, I have these assets and I have these different ways of investing them. Give me the best possible plan for investing that's going to maximize my returns while mitigating my risk. Another classic example of a mathematical planning problem. Then you have the power industry. A lot of what happens in the power industry is they have to make plans about, hey, this is what the power demand for tomorrow is going to be. How are we going to generate that power? And then how are we going to ship it around the country given the capacity of the power lines? And so you're always having to constantly adjust your power delivery plan. And this is actually like I said, one of the heaviest users of mathematical planning. And then there's retail, another industry that I've worked in, and a classic example of I have these goods, I need to transport them to a warehouse, and then I need to move them from the warehouse to either a retailer or to a person's home. What plan for moving the goods is going to provide the best experience for my customers while also meeting requirements of on-time delivery? Another perfect example of a mathematical planning problem. And many more. Yeah, but these are just 4 examples, but almost every industry that I've worked with or consulted with has had these kinds of problems. They just didn't realize it yet. And I'm hoping by the end of this, you're going to see the opportunities in your own workplace or wherever you volunteer, where like, hey, we have an opportunity to use mathematical planning to make decision-making easier for people. And this is the part where I want to start to disambiguate mathematical planning from machine learning. And the artificial intelligence is this really broad term. And I realize I'm taking a little bit of liberties. I don't have a PhD in AI, so maybe I'm not qualified to make this distinction. But I think of artificial intelligence as this very broad umbrella. And mathematical planning and machine learning both fall underneath that umbrella, right? But they are not the same thing. The key difference is mathematical planning answers the question, what should we do? Versus machine learning, which answers the question, what is most likely? Like, hey, what is the most likely thing to happen? It's trying to make a prediction about the future, whereas mathematical planning is more about, okay, what set of actions should I take? And that's where the big difference is between them. So they're often used together to create even more powerful solutions. And this is where I say, these things are not opposed. They have to actually work together beautifully. So mathematical planning with machine learning is a beautiful thing. In a couple industries where this happens all the time right now is, I'm going to go back to the power generation example. So in the power generation industry, the power industry, they will have a machine learning model of some type, which makes predictions about the future. Like tomorrow, the weather is going to be this, the season is this, the temperature is going to be this, the density of the population is this. And so it's saying like, I predict that this is what the power requirement is going to be in these areas tomorrow. Okay, given that prediction, give me a plan that is the most efficient way to deliver that necessary power, right? Machine learning model makes a prediction, and then the mathematical planning model then says, okay, given that prediction, this is the best possible plan to meet those requirements. And then on the flip side, we can come back to the freight industry, where you have mathematical planning feeding machine learning. And so freight industry, they have a bunch of freight they need to move from different locations. They create a plan based on those requirements. And then they feed that plan into a machine learning model, which says like, okay, I predict that your on-time delivery is going to be this based on the things that I am saying, right? Okay, there's these types of weather conditions. There are these types of delays. So I think that probability of this package arriving on time is 95% or 80%, whatever it may be. But again, that's a case of we take a plan and then we feed that into a machine learning model. That machine learning model then gives us predictions about what are the likely outcomes. So these techniques are different, but highly complementary. And that's how we actually use it quite a bit in our industry. So now the question comes to, okay, cool. You've described mathematical planning, you've contrasted it with machine learning, but like, how do we actually do this? How do we actually solve these mathematical planning models? This is all very abstract, Matthew. Well, right now, a lot of what people do when answering these things is they try to use Excel, and they have some expert user who has a bunch of data in some file, and they filter and sort and they make decisions, and it's very painful process that they go through. Well, painful for me as I watch, like, what are you doing? It's going to be so much easier. And so that's how they're solving these problems right now, is they're using Excel and an expert user and some procedure that they follow to make decisions. And as I've kind of worked in different places, I've kind of come away with what I call the cruise conjecture, which is kind of a silly thing, which at the heart of every business of significant age and or size is an Excel app, right? There is some Excel file somewhere that some expert knows how to use. And this is frightening, especially if you have to debug it. And so part of what I love to do is go and look at these processes, these decisions that people are making using Excel, and turn them into mathematical planning models, which are more reliable, faster, and can be source controlled and managed much more easily. And so this is one of the key things that we do is whenever we see some expert user using Excel to make critical business decisions, we're like, that's an opportunity for a mathematical planning model, because if that person leaves, we're in trouble. So then we need to say, how do we turn these decision-making processes that we're doing in Excel, how do we turn those into models? And what I would like to do is kind of take us through that process, a very simple model. And so this is where my warning comes in. These models will start very simple. They will get more complex. So don't worry. So first example I like to use is the food truck example. I live in Portland, Oregon, United States. And for those of you who may or may not know, we have lots of food trucks here. It's very popular. And so one of the silly examples I like to use is what I call the food truck planning problem. And we're running a food truck. And at the beginning of the day, we need to decide, what are we going to pack into our food truck for us to sell during the day? And right now, we sell tacos and we sell burgers. We make $1 for every taco that we sell, and we make $2 for every burger. We have 200 taco shells available to us, and we have 300 burger buns, like in our warehouse. We're not well stocked, clearly. You can only carry 450 pounds on this food truck. My apologies to people not in the United States. We're using imperial units. My apologies. can only pack 450 pounds on our food truck. It's a very small food truck. And each taco requires 1.5 pounds of toppings, very big tacos. And each burger requires 1 pound of toppings. Okay, very simple word problem. So let's talk about what are the components for this model that we're gonna create based on that description. We have decision variables. So these are the choices that we need to make. We have an objective, which is how we measure success. And we have constraints. And these are the rules that we need to obey. So in our case, I'm going to kind of draw this out so we can visualize it. On the horizontal axis, we have number of burgers. And at the vertical axis, we have number of tacos. And now I'm going to kind of visualize that problem by drawing some things on this page. If I draw the taco constraint, I only have 200 shells. So my solution has to be below this red line, which is why I have a red line and an arrow pointing down. So I know the solution is going to be below this line. I also have a limitation on the number of hamburgers I could possibly pack for because I only have 300 buns. And so that's visualized as a vertical bar with an arrow pointing to the left, saying, hey, my solution needs to be the left side of this constraint. So like this is like the wall I can't go over. And then I have the weight that the food truck can carry, which is this horizontal line, this diagonal line. That diagonal line is basically what the weight limit is. If you had just tacos, you could pack up to 300 because of weight. If you had just burgers, you could pack 450 because of weight. I believe it's 450. But the solution is going to be below this. So these 3 red lines are the constraints of my problem. The solution has to exist in this space defined by those 3 constraints. And then if I draw how I measure success as an arrow, so this is the objective. I get $1 per taco and $2 per burger. So that's why the green arrow is pointing that direction, saying like, hey, this is the direction of success. I want to go as far in this direction as possible while staying within those boundaries. Now, visually, we can see the answer to this because it's such a simple problem. It's only 2 dimensions. It's like, well, the best possible solution is going to be 300 burgers and 100 tacos, and that will give us a revenue of 700. Okay, we have visualized it. Now, if we kind of write that description out, we're going to say, hey, we're going to have a few different decisions, the number of burgers, the number of tacos. Our objective is to maximize revenue, which we calculate using $2 times the number of burgers and $1 times the number of tacos. We have constraints, which is the max burger, which is what we visualized. It's going to be less than or equal to 300. Max taco is less than or equal to 200. And then we have our weight constraint. So let's write some code. Now, if you want to code along with me, you are welcome to. You also don't need to. If you clone the repo and you open it up, you're going to see something like this. Most of this content here is a presentation that I'm giving right now. If you go into code, and if you go to F# Visual Studio, that's what I will be using. Go ahead and open that up. Optimization 101. Give Visual Studio a moment here to catch up. And then you're going to see the solution. There's the practice. Come back. There's the practice, and there are solutions. So for those of you who just want to see what the end looks like, you can just jump to solutions. If you're wanting to follow along, you can start with a practice. And so we're going to go to the practice one. And this provides all the comments to say like, hey, this is what you need to do to solve this problem. So what I'm going to do now is kind of implement that model that we just described in code and say, hey, I need to create a decision variable for the number of burgers. We're using the flips library, which is an F# library for doing mathematical planning that came out of Quicken Loans. And so if you want to read up on that, the documentation, that's what I'm using. These techniques and these ideas translate to any library which allows you to do mathematical planning. So Aptano is another one for .NET. Garobi has one for Python. There's also Pulp. There's a bunch. So don't feel like this only applies to this library. So let's say let number of burgers equals decision create. In this case, we're going to say continuous, and we'll get to what that means later and say like, hey, number of hamburgers is going to be between 0 and infinity. And if I hover over this, is a function, it takes the name. So what I'm naming it, it's lower bound and it's upper bound. And saying like, hey, you're going to have a decision. It's for the number of hamburgers, and it could be anything from 0 to infinity. And then we're going to do the same thing for tacos. Let number of tacos equal decision create. That's how you know it's live. Number of tacos, and again from 0 to infinity. Great. We now have two decisions that we can work with. Let's create our objective expression. So this is going to be the kind of expression that the solver, so the solver is the engine underneath everything that finds these solutions. The objective expression is how we're telling it, this is how you measure success, right? This is the thing I want you to use to say whether something is better or worse. So let objective expression equal 2.0 times number of burgers plus 1.0 times number of tacos. So this gives us, if I have a linear expression, don't worry about linear right now, but basically it's saying like, hey, this is what you're going to use for evaluating the quality of the solutions. And then I'm going to create an objective here. So let objective equal objective create, give it the name maximize revenue, maximize, and then the objective expression. So here I'm giving it the name of the objective. I'm saying I want you to maximize this expression. I want this to go as high as possible. And this is the thing that you're using to gauge success. Great. We have an objective. Now we need to create some constraints which put boundaries on the solution. So it's saying, hey, let max burgers equals constraint create max burgers, and say number of burgers is less than or equal to 300 per the description of our problem. Then we do the same thing for tacos. So if we hover over this, is like, hey, this is a constraint, this thing you just made. Say let max tacos equals constraint create max tacos, number of tacos less than or equal to 200. Great. And then we need our constraint for the weight. So let max weight equal constraint create max weight. And this is going to be 1.5 times number of tacos plus 1.0 times number of burgers to be less than or equal to 450. And then we want to actually create our model, which is the thing that kind of brings all these pieces together into a single thing. So let model equal model create. And to create a model, the first thing you do is you have to give it an objective. Like, hey, I'm going to create a model object, and I'm going to give you the objective, which is how you measure success. Objective. And then F#, because I'm using the F# language, the pipe operator is basically take that thing and send it into this next function. It's a lot like method chaining in C#, if that's what you're used to. It's very similar. So model, add constraint. In this case, I'm adding the max burgers. So what that does is it takes the model object that was created here and then adds the max burgers constraint to it. And then I'm going to model.add constraint, max tacos, model, add constraint, max weight. I know the model's very simple. Don't worry, we will scale. It will get more complex. So we are now we created a model, we added constraints to it. I'm just creating some settings I'm going to give to the solver. One way I like to think about mathematical planning and the whole workflow, it's a lot like writing queries for a database. SQL is a declarative language for what the result set looks like, right? It's like, hey, I want to do some joins and do some where clause and some filtering and stuff. We're doing something very similar. We're building this model, which is a description of what we want. I want a solution that obeys these constraints, but give me the best possible value given these constraints. And so we're going to create this model. We're going to give it to a solver, which is like a database query engine, which is then going to execute it, and then it's going to give us a solution back. Very similar workflow. So now I'm going to say like, hey, I want to get the result. So the result equal solver.solve, and this is the function that actually takes those settings in that model and gives us a solution back. So it takes settings. Don't worry about these. It's just basically saying what engine I want it to use underneath. Give it the model, and this is going to give me some results back. And then I'm going to make my life easy, and I'm going to say, hey, if you get the solution back, print out those results so we can look at them. And we should get the exact same thing that we saw in our visual description. If not, we have a problem. So what I'm going to do, I'm going to come up here to console runner, and I'm going to uncomment this model here, right? And then I'm going to press F5 and see what happens. And I'm going to drag it over. And what we see is that, hey, here's the result. 700 in revenue, and number of hamburgers is 300, and number of tacos is 100, which exactly matches what we saw visually. Yay, congratulations. Our first model. We feel great. Now, let's talk about what just happened. How does this work? Right. And so I think as developers, a lot of the time we'd like to understand our tools and what's going on underneath the hood. And I always get really fascinated and geeked out about this. So I like to know, like, how does it know that's the answer? How did it find that solution? Well, if you go on Wikipedia and look up linear programming, which is kind of a subset inside of this field, you're going to see this really technical definition. More formally, linear programming is a technique for optimization, linear objective functions, linear equality, linear blah, 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 convex polytope, half spaces. Oh my goodness, what on earth is going on? Very technical description. Let's break down what's happening. So if you remember this diagram, we had a set of constraints. We have an objective, which is the direction we want to go. And you notice that the solution was at this corner, right? This is the best possible value. That's really significant that it's at a corner, which is these two constraints come together and create this corner. And you notice that there's several other corners that are defined by these intersections, right? Several of them. Now, solvers take advantage of these corners. What they do is kind of like the simplified description that I like to give people. And of course, you'll notice the asterisk at the end. A solver searches the nodes that are defined by these intersection of constraints until it cannot find a better solution. That's just another way of describing a tree search. Is essentially what's going on. Is it's going from like node to node and saying like, hey, are there adjacent nodes? Are those adjacent nodes better than the node I'm currently at? Yes or no? If it's better, move. If it's not, oh, I must have found the best solution. If there are any hardcore optimization people and you feel that was too simplistic, I left myself an asterisk, so don't worry. There's more to it than that, but that is like the simplified version of what is actually happening. So let's do another problem, just so we kind of get this into our hands, get this into our head. And I call this the running a farm model, right? And I realize no one has like piped in yet. If you have a question, or you want to get my attention, please feel free to just unmute yourself and just jump in with a question. I'm not going to lose my spot. And I would much rather answer questions in the moment than, we wait till the end and then you forget what it is that you're going to ask. If you put your question in chat, I'm going to have a much more difficult time seeing it. I have it open, but it doesn't necessarily draw my attention the same way someone actually unmuting and speaking to me. So feel free to jump in, whatever. I would love to clarify things as we go along. But you also don't have to. I'm hoping that this is translating. Sometimes I'll ask for feedback, say like, hey, is this making sense to people? Because it's a little, I really appreciate nods from people. I can see those because most of the screen is just a blank wall of text of people's names, but that's great too. So we're running a farm, right? And we're raising cows, pigs, and chickens. We earn $100 per cow, $50 per pig, and $8 per chicken. We have 1,000 acres of pasture. It takes 1 acre per cow, 0.2 per pig, and none per chicken. We just have a chicken yard. We have 100 tons of feed. Cows don't take any feed. They just live off the pasture. Pigs take 1 ton, and chickens take 0.1. We have 7,200 hours of labor available. Cows take 9.5, pigs take 8, and chickens take 0. Clearly, I have not been raised on a farm. These numbers are for the example. Don't judge me. So, running a farm model, let's take that word description and turn it into some notation, some types for us. We have number of cows, which we're going to call cows, pigs, and chickens. We have an objective, which is maximize our revenue, which is 100 per cow, 50 per pig, and 8 per chicken. We have constraints, which are the total amount of pasture available to us, the total amount of feed available to us, and the total number of hours available to us. So let's turn that into some code. Coming back over here to Visual Studio, I'm going to comment out that model. I'm going to uncomment the farm model and jump over here to farm model. And I need to create my decision variables for cows, pigs, and chickens. So let cows equal decision create continuous number of cows. We can go from 0 to infinity. That'd be a lot of cows. We have pigs. Decision create. I want a continuous one. I really want a continuous one, so we'll just do it by hand. And number of pigs goes from 0 to infinity. And chickens equals decision create continuous number of chickens to infinity. Great. Now we need a way to measure success. So the objective expression. So objective expression equals 100 times cows plus 50 times pigs plus 8 times chickens. And then I need to create an objective using that expression. So let objective equal objective create maximize revenue is the name. I want to maximize, and here is the expression I want you to use. Great. Same thing as before. But now we need some constraints to define the boundaries on our problem. The first one is going to be max pasture, which constraint create max pasture 1.0 times the cows plus 0.2 times the pigs less or equal to 1,000 acres. Great. Now we need one for the feed. So let max feed equal constraint create max feed. This is going to be 1.0 times pigs plus 0.1 times chickens less or equal to 100. And then max labor. Constraint, create max labor. 9.5 times cows plus 8.0 times pigs less or equal to 7,200. Now we need to create our model object, which brings all these things together. So let model equal model create, and I'm going to give it the objective. I'm going to pipe that in, say model add constraint max pasture, model add constraint max feed, and then model add constraint max labor. So now we have a model object with the objective that we've given it and the constraints, the limitations on the solution. We have the settings that were exact same ones that we're using before, and let result equal solver.solve using those kind of default settings and the model. And I'm going to go ahead and make my life easy and uncomment this. There we go. So now if I run that, I'm going to get a solution which says, hey, you should raise 1,000 chickens, 757.89 cows, and no pigs. And that'll give you a revenue of 83,789. Fantastic. Now, we just did that, and some of you are probably already like, oh my gosh, Matthew, this is really painful, because the way we're coding this is not scalable, right? Every time we want to add an animal, we're going to have to like create another decision variable and like manually add it to these expressions. Like this is a very clunky way to do this. I wish there was a way that was more scalable and allowed us to kind of like arbitrarily add things to our model and have it just work. And I was like, you're absolutely right. Wouldn't it be nice if there were some tools that allowed us to do that? So now we're going to add some things to our repertoire to make expressing these models much easier. I'm seeing some people make some comments about linear programming. You're exactly correct. That is what we are doing. Mathematical planning is just kind of like a broader term. Inside of it is linear programming. So very insightful. So first thing we're going to talk about is sets. Not necessarily like the strict definition of a set, but just the idea of like, hey, we have sets of values, and those things are what we typically index our data by. This presentation is meant to be slightly language agnostic because I give it using Python or C# or F#, depending on the company that I'm working with. So whatever language, whatever data structure is in your language that gives you a unique set of values, use that. But it's how we index our data. So for example, things like cities or items or times, but it's how we index into our collections to get the data. And we have parameters. And these are the numbers that actually go into the model. So things like costs or revenue per animal or amount of land per animal. And it's typically stored in either dictionary or map, an associative array, whatever it is in that programming language that you're using. In Python, it looks like this. But sets are those values that we index our data by. The parameters are stored in dictionary-like data structures that we can easily index into it, because it's going to allow us to create models which scale very easily with the amount of data. And so we now kind of have an upgraded list of things that kind of go into a mathematical planning model. We have sets, we have the parameters, and then we have the decision variables, the objective, and the constraints. And so those things together kind of like the basic ingredients for creating a mathematical programming model. So I'm going to revise that farm example into something that's going to scale much more easily. And so I have my sets. So now I have a set of animals, which is cow, chicken, and pig. And I have parameters, which is revenue, which is a dictionary, which I index by animal. And there's the revenue associated. Pasture for each animal, feed for each animal, and the labor for each animal. And my parameters are now got total amount of pasture available, feed, and labor. And so my decisions are how many for each animal. I still want to maximize revenue, but I'm now going to make it something that scales with the number of animals. And my constraints are the same with the sum of the pasture, feed, and labor. That has to be less than or equal to the totals. So let's go back to that model and revise it. And I'm going to go ahead and comment out this one and do a revised farming model. So I provide all the data that you need here if you're doing the practice, but now I have this like list of animals, cows, pigs, and chickens. I have my revenue, which I'm storing as a map. So in F#, a map is a dictionary-like data structure. It's backed by an AVL tree for those who care. But it's typically the idiomatic data structure to use in F# for this type of data. And so it's indexed by a string, and the value inside of it is a float. And then I have pasture, which is the same thing, feed, and then labor. It's all the same data. And then I have my total pasture, total feed, and total labor. So now let's reformulate that problem, but in a more scalable way. So I'm going to use some of the features of flips now. And so let animal decisions. And I'm going to use something called a decision builder. For those of you who care, it is a computation expression. If that doesn't make any sense to you, don't worry. You don't need to know it. Just there for the curious. And what is going to happen is I'm going to create a set of decisions, and this thing is going to automatically name them for me. So I'm not having to say like number of chickens, number of cows, or anything like that. It's just going to do that automatically. So I can say for animal in animals, I'm going to say create a continuous decision variable that can go from 0 to infinity. And I should be able to spell continuous. There we go. And I am going to put that into a map. So this thing is saying, like, hey, I'm going to create a decision associated with each value in animals. Is going to be a continuous decision, and it can range from 0 to infinity. And I am going to automatically name it for you using this as the prefix. So it's just kind of taking some of the annoying management out of our hands and just making things more straightforward. So now I have my animal decisions stored in a map, which is a dictionary-like data structure. And now I want to create an objective expression. I'm going to do this a little bit differently now. So objective expression is equal to, and for key value, and this is animal decision variable, in animal decisions. So this is kind of a list expression here, very similar to what you would be doing in Python. I want you to look up the revenue for a given animal and multiply it by the decision variable associated with that animal. And then I want you to sum that up. Right. So now for however many decisions that are in that collection, I'm just going to go through each of them and then multiply the associated revenue with it and then sum that all up. So now this can scale to however many animals I add to my data. So again, create the objective, create, maximize revenue. Someone have a question? I think I heard someone come off of mute.
Yeah, Matthew, I was just curious. The animal reference in your for loop, does that need to be returned at all in the decision builder?
Oh, no. So no asterisks, right? So this is a fantastic question and gets into what are computation expressions. So F sharp behind the scenes takes everything between these curly braces and kind of does work with that expression. And behind the scenes, it actually has access to that variable, which is why when you come out here, so animals is a string list, right?
Yeah.
This thing is a map of string to decision. So when this thing, it takes this expression, computes it, and inside a decision builder, it does have access to animal. It does
So
actually have.
So it knows that animal is the context of that
Yes.
body of the for loop. Got you.
Yes.
Yeah, nice
Yes.
one.
Yes. And so if you ever go look at flips, and if you've ever worked with Pulp, which is a Python library, or Groby Python, the flips library is heavily inspired by those and tries to duplicate a lot of the functionality inside of there. And so that's what's going on. So it knows, hey, for each animal, I'm going to make a thing, and then I'm going to return to you in this case, it was a sequence of tuples, which is the animal and the decision associated with it. But then I immediately put that into a map because that's how I want to work with it. That's a really fantastic question, though. This is just kind of like, we're just going to do some magic here to make your life easier.
Awesome. Thank you.
Thank you for asking. I love clarifying things for people. So I've created the objective expression. I've created my objective object. And now we need to create some constraints. So here, I'm going to kind of, and again, the sophistication of this thing is going to evolve, and I'm doing some things to just kind of like make it very clear what is happening. So if you're like, oh, this is kind of clunky, don't worry, it'll get cleaner. So now I'm going to have my pasture expression, and I'm going to use that same list expression technique that I was using before. So for animal in animals, again, this is going to feel very Pythonic for people who've worked with Python. So pasture, and I like Python, by the way. I'm not hating on Python. Animal.
Excuse me if I interrupt you.
Go for
The
it.
objective isn't finished, isn't it?
Oh my gosh, thank you. Love pair programming. Thank you.
Yeah, I was just wondering if there's additional magic happening I wasn't aware of.
No, I'm so glad you asked that. Thank you. Nope, it was not done. It is done now. Thank you for calling that out. So now we have a pasture expression. So very much like how we did the revenue, now we're doing it for pasture. We're going through each of the animals, and we're saying like, hey, the pasture associated with the animal multiplied by the animal decision. Like how much of that animal are we going to decide to raise? And then I'm going to say list sum. And now I need to take that expression and create a constraint with it. So let max pasture constraint. And again, I'm just spelling everything out in lots of detail for people to follow. Create max pasture. And now I'm going to say, hey, pasture expression less than or equal to total pasture. This will get even cleaner as we go forward, but I'm stepping up the features as we go. So now I need to do the same thing for feed and for labor. So let feed expression equal for animal in animals. Feed animal times animal decisions. Someone else come off of mute? Nope. Okay. Feed max feed constraint. It really wants to do const. Come on, Visual Studio, you're killing me. Max feed, and then feed expression less than or equal to total feed. And then finally for labor, we have for animal in animals. We're going to have the labor given animal times the decision associated with it. So animal. And then we want to sum that up. Seriously, I do want to sum it up. And then max labor constraint. Constraint, create max labor expression less than or equal to total labor. Fantastic. Now, the nice thing now is that as we add animals to the input, to the parameters, we wouldn't have to change our model. We wouldn't have to do any kind of refactoring. And so for me, that's often the goal when putting together models, like creating in such a way that it's just going to flex automatically with the size of the input and the dimensions. So let model equal model.create and objective. Going to then add our constraints, add constraint, and this is the max pasture, model, add constraint, max feed, and model, add constraint, max labor. All right. We've got our model, which takes our objective, our constraints. Now we want to solve that thing. So let result equal solver solve settings model. Again, making my life easy, but just uncommenting. And we'll go ahead and run this and see what happens. Hopefully, we get the same result. Otherwise, I've done something terribly wrong, and we're going to have fun debugging it. Fortunately, the debug gods have been kind to me today, and we get the exact same result. 1,000 chickens, 757 cows, and a revenue of $83,789. Now, why did I go through that exercise? To show you, like, hey, there are things that we can do to make it so our models can flex and grow with the size of the data and the dimensions. And so this is much more of like what we would want to be doing as we create more and more sophisticated models. So we are now at, well, the top of the first hour. I don't know what time zone you're in. It's 10 a.m. here now. So we're going to go ahead and take 10 minutes. And I will see you 10 minutes from now. So 10 a.m. Pacific Standard Time. So feel free to get up, stretch, refill your coffee you need to, and I will be back in just a few minutes. So as someone pointed out, never heard of raising part of a cow. Not a thing. That's kind of weird. And so wouldn't it be nice if we could write a model such that we actually get correct results, like meaningful results? Because you might be able to say, hey, I can just like round down the number of cows and that'll work. But sometimes that isn't always correct. And sometimes that'll give you invalid solutions. And so we'd really want to be able to model, integral values. And when it comes to mathematical planning, and as some people are pointing out, linear programming, integer programming, mixed integer programming, those are all kind of part of the same sphere of terms. The reason I say mathematical planning is because it tends to land with business users more clearly. If I use the word programming, everyone assumes that I'm talking about code. And it's because programming used to mean planning, and these terms came into existence before computers. Now that word has kind of changed meaning in our society. So that's why I like to use something a little bit different, just to, again, kind of tell people like, this is something a little bit different. And this is what I'm talking about. So in this domain, we have different types of decision variables. We have continuous, which is what we've been using. And we typically model that as a float, right? It's like it could be any value between a lower and upper bound, right? Which is a great default to use for a variety of reasons. And we'll get into why later. We also have integer decision variables where you say like, hey, this thing has to take on integral values, right? It's not continuous. It's got to be an integer. And we also have binary decision variables. And once you have binary decision variables, things get really interesting because now you can start modeling logic. And if you can model logic, you can model like business decisions and business strategies and things like that. So when you have those binary decision variables, you can do things like and logic. You can model ORs. You can model XORs. You can model XNORs. And you can model NANDs, right? So if you're saying like, hey, I have these conditions and I could have very tight control over what is true at any given time and what conditions are mutually exclusive, or if this, then you must do this as well, that type of logic. So let's look at a problem where we utilize this. And again, I'm from Portland, Oregon, and we love our coffee. And so we have to have an example in here where we talk about roasting coffee. So this is the Portland Roasters Inc. problem. And we need to do some planning for our warehousing capacity and our roasting capacity. And we need to find where to build our roasting plants and our warehouses in the city of Portland. We need at least 30 tons of roasting capacity. We need at least 30,000 square feet of warehouse space. And wherever we build a roasting plant, we also need to build a warehouse. So this thing's a little different than what we've shown so far. This is a piece of business logic saying like, if you do this, you must also do this. Interesting. But there's not a requirement like if you build a warehouse, you also need a roasting plant. No. It's just if you have a roasting plant, you must also have a warehouse. So let's talk about this. So we have a set of locations. Our parameters are the roasting cost, the cost to build a roaster at a location, the cost for building a warehouse at a location, the roasting capacity for a location, because different locations have different amounts of land available to us. So how big of a roaster can you build? And the warehouse capacity for a given location. And then we have what our min roasting capacity is and what our min warehouse capacity is. Great. What are our decisions? Well, we have, do we build a roaster or not? It's going to be one of our decisions, and it's going to be binary. 0, don't build the roaster here. 1, build the roaster. We have our build warehouse decisions. 0, don't build the warehouse. 1, build the warehouse. We have an objective. We want to minimize our cost. Right? We want a building plan that's going to meet our requirements, but be affordable. That's the cost of the warehouses plus the cost of the roasters. Constraints are the min warehouse capacity. So the sum of how many warehouses you plan has to be greater than or equal to the minimum warehouse capacity. You have your min roaster capacity. So the sum of the roasting capacity that you build has to be greater than or equal to the min. And warehouse required for roaster. For each location, if you build a roaster, you must have a warehouse. Interesting. Let's do it. So pumped right now. Gonna comment out this one. Gonna uncomment this one. Jump in solutions and go to the coffee model. So in here, I have some data already. And for anyone who's ever been to Portland, you may recognize some of these neighborhood names. So these are actually locations around here. You have what the roaster cost is. So if I build a roaster at this location, it's going to cost me this much. I have my roaster capacity. So if I build a roaster here, this is what capacity it will give me. I have my warehouse cost for each location, for a location, what the cost is, and the warehouse capacity associated with each location. And then I have my min warehouse capacity, my min roasting capacity. Okay. Let's do this. So pumped. Okay. Roaster decisions. I'm going to be using that decision builder again. It's going to be build roaster. And I'm going to say, hey, for location in locations, I want a Boolean. So what's happening here? It's saying, hey, you're going to go through each location in locations and create a decision that's going to be Boolean, 0 or 1. And then I want to put that into a map. So now I have something that is a map. It's indexed by the location, and the value associated with that index is a decision. In this case, is 0 or a 1. So those are my roaster decisions, but I also need warehouse decisions. So warehouse decisions is equal to decision builder, build a warehouse for locations, do a thing. Again, Boolean. And I want to put that in a map. So these decisions are associated with, do I build a roaster at a given location? And these are, do I build a warehouse at a given location? 0 indicating nope, 1 indicating yes. Now to create variable, oh, should have read my own comments. Create an expression for the cost of the warehouses. So let warehouse cost expression equals for a location in locations. I need to do a thing. I'm going to say warehouse cost times warehouse location times warehouse decision associated with that location. And I want to sum that. So this is going to give me, hey, if I build it, this will have to be a 1. 1 times whatever the cost is going to give you that cost. Then I'm going to sum all that up. But if I don't build it, it's going to be a 0. So 0 times the cost is still going to be 0. And I am going to make a roaster cost expression. Roaster cost expression. Look very similar. Location in locations. Roaster cost for a given location times roaster decision for that location. List sum. Summing up the costs associated with all of my decisions to build roasters. And now I'm going to create whatever that total cost is. Total cost expression is just equal to warehouse plus roaster. So that expression is going to be what the total cost of my plan is. And now I want to create an objective. Minimize cost, minimize, and then total cost expression. There we go. Now I need an expression for total roasting capacity. So let roasting capacity expression or location in locations. Roaster capacity for a given location times roaster decisions for a given location. And now we're going to create a constraint which says, okay. let. And roaster capacity, roaster this expression has to be greater than or equal to min roasting capacity. And then I need an expression for warehouse capacity expression. And this is going to be for a location. In locations, going to be warehouse capacity, location, warehouse decisions for location, list sum. Now we need to create the constraint for that. So warehouse capacity constraint, not const, constraint, create min warehouse space. It's going to be warehouse. This expression must be greater than or equal to min warehouse capacity. Now we come to something a little bit different. We need to create a constraint associated with each location which says, like, hey, if you build a roaster, you must also build a warehouse. Interesting. Okay. Well, probably know the name, warehouse and roaster constraint equals a thing. Now, again, we're going to use another one of the features of the library to make our lives a little bit easier. It's the constraint builder. Warehouse and roaster coexist. How is this going to work? So I'm going to say, hey, well, for each location, in locations, I want to do a thing. I want to create a constraint. And in this case, what I'm going to say is like, okay, well, if I have a roaster decision at a location, and I have a warehouse decision for a location, these things need to relate to each other in some way. Like, okay, what would that be? Okay, so let's talk through this real quick. If this is a 1, which means build it, this also has to be a 1. If this is a 0, this could be a 1 or a 0. You don't have to build a warehouse if you don't have a roaster. So we need something that says, okay, if you build the roaster, you must build a warehouse, but if you don't build the roaster, you don't have to. So the question is, what operator makes these two Boolean binary decision variables behave that way? If this is 0, this can be 0 or 1, because 0 is less than or equal to 0 or 1. If this is 1, is 0 less than or equal to 1? Sorry, my mistake. If this is 1, is 1 less than or equal to 0? No. So if this is 1, this must also be 1 for this expression to hold, for this comparison to hold. That's how you can model that logic. If this is 1, this must be 1. But if this is 0, this could be 1 or 0. Is this landing for people? It's a little funky to think of that way. Go ahead.
It's easy to understand it now, but it wasn't something that came up at the first question.
Yeah, no, for sure. And that's why I like to pause here for a second sometimes when you're modeling things, if someone comes to me with like business logic, like, hey, we want to model these business decisions. Like if we do this, we have to do this, but all these kind of conditions, it can feel a little clunky to model that sometimes. It can feel a little odd, but you can do it. And sometimes you have to kind of do these like little mental exercises where you like kind of look through like, hey, if this is this and this is that, like, is this going to hold or not? But you absolutely can do it, which is the point I'm trying to make here. So what does this do, right? So constraint builder, what it does is, again, you're giving it a prefix for naming these constraints, because before we'd have to like give it a name. Now it's like, oh, okay, I see what you're doing. Here's the prefix for the naming. You're going to create a constraint associated with each location. And so I'm also going to use that for part of the name. And this is what the constraint expression is. This is what the comparison is that I'm creating. And so this is going to create a sequence of constraints, because it's going to do this for each location automatically. And it's going to take care of the naming for me automatically, because I am lazy. So now we need to build the model. Bring that all together. So let model equal model create. And we have our objective. Model add constraint, where we need to add roaster capacity constraint. Oh yeah. Model add constraint, warehouse capacity constraint, and model add constraints, plural, warehouse and roaster constraints. And really this should be a plural, my bad. So now we create a model with our objective of minimizing the cost. We've added our roasting capacity, our warehousing capacity, and the fact if you build a roaster, you must also build a warehouse at that location. Same default settings, nothing new there. Let result equal solver solve settings model. And again, I am lazy, and I'm just going to uncomment that. Make my life simple. Come back here and make sure that's the thing I'm doing. I'm going to press F5. And if I did it correctly, we will get an answer. Okay, I have an answer. Yes, it's a little clunky. I'll make it prettier next time. So my apologies. Now, the important thing is, hey, these are all the values. It said, hey, if we built a roaster, did we also build a warehouse down here? So we built a roaster at St. John's, which is a neighborhood around Portland. We also built a warehouse at St. John's. We built a roaster in Hawthorne. We also built a warehouse in Hawthorne. But we also built warehouses in Alberta and Selwood, because we built the two roasters. We built two warehouses next to them, but we still didn't have enough warehouse capacity. So we needed to build some additional warehouses to meet that min warehousing capacity requirement. But the important thing is, we built warehouses wherever we needed to build roasters. And if you go and look at the data and the costs associated with the locations, those are the St. John's location is not the cheapest place for a warehouse. Right. So if you're like, oh, well, Matthew maybe just defaulted to that because it was cheaper. No, it's not. That is not the cheapest place for warehouse capacity in this model. You can go ahead and check that. And it's the purpose to illustrate that, yeah, this business logic is actually having an impact on the solution. It's forcing you to build there as well. Well, cool. That was neat and all, but make sure this is where I'm at next. Yeah. So you remember how I mentioned, like, we're going to kind of keep adding layers, kind of keep adding features. We are writing this a lot. This like for location and locations, blah, blah, blah. For location, locations, blah, blah, blah. For location, location. Oh my goodness. This is getting cumbersome. I'm getting annoyed and I'm lazy. I don't want to have to write so much. Wouldn't it be nice if there's a data structure for mathematical planning that made it all a lot cleaner and easier? And my answer would be yes, absolutely. I would like something that would make kind of expressing those sums more succinct and easier. So we're going to take a slight detour and talk about that a little bit so that we can make our lives more straightforward. And I call it the slice map detour. So we have been doing a lot of stuff like this. So I can go ahead and run this code. It won't be terribly exciting though. It's more to show you what this is doing. So we've been doing this type of thing. We have some indices. We have, in this case, a map where the index is an int and the value is a float. We create some decisions. We put those in a map, and then we want to sum that up. We're having to write list.sum, or in this case, the way we've been writing it is like this, list sum. Those are functionally equivalent. They do the exact same thing. It's just in this case, I'm using a pipe. But the point is we're having to write this over and over and over and over. That gets really annoying. What if we had something more straightforward? So fortunately, the library has a set of data structures called the slice maps, which make doing this more straightforward. Go ahead and open that up. Not going to be terribly exciting, but a slice map is basically a map, but it adds slicing, so you can slice along dimensions much more easily, and it makes summing a little bit easier to express for someone who comes from kind of the mathematical planning optimization side. So now what we can do is saying like, hey, we can say, hey, I'm doing the exact same thing that I was doing up here, saying like, hey, instead of storing this in a map of int float, I want you to store it in a slice map. And I'm creating my decisions as I did before, but instead of putting them in a map, I'm putting them in a slice map. And then it allows me to do this, where this, if you've worked in MATLAB, you may recognize this. The highfalutin term is the Hadamard product. But what it is doing is it says like, hey, I understand you have these slice maps. I understand how they're indexed. And kind of like in SQL doing like an inner join, it's going to go through the indexes of them and say, hey, where these indexes match up, I'm going to multiply the values together. And that produces a new slice map with where the overlapping keys are in there. And then there's also a sum function which is added, which knows how to work with all the slice maps, saying like, hey, this is done so much, we're going to make it easy on you. Sum the kind of inner join product of the values of these two slice maps and put that all together. So instead of having to write this all the time, you can write this. Bit more straightforward, and it takes care of the joins and stuff for you, so you don't have to worry. And it also takes care of empty data, because right now, if we went through right now on maps have had a value for every single index, what if there wasn't a value at that index? You would get an error here where like, oh, you're trying to access something where there's no value at that key, at that index. This just does that correctly based on this domain, this problem space. So now the other thing that you can do, if I have a set of cities and items and I have item cost, I turn that into a slice map, indexed by string and float. You can access items just like you could with a map. But now you can also slice the data, saying like, hey, I actually just want everything that's greater than A. Right? So it would return this subset. Because these are all the keys, because you're slicing on the key of the collection. I want everything greater than A, so you would get B through E and their values associated with it. You could also say between, like, hey, I want B, C, and D, right? So you can take a slice and just do like a subslice of it. So all kinds of different ways of slicing and dicing along dimensions you can do. And this is going to get really useful later. But you can also, go ahead.
Sorry
Go
to stop you. Can you go over the slice map one more time? I got lost. Sorry.
Yep, for sure. And I'm not done either. So I'm just going to kind of keep going because I'm still kind of addressing that. Slice map is for when your data is indexed by a single dimension. But there's also 2-dimensional data, 3-dimensional data, 4-dimensional data, 5-dimensional data. And so this data is saying, hey, I have an item location and a cost. I have like the item location as how you key this data. It's 2 dimensions and there's a value associated with it. I can put that into a slice map. In this case, a slice map 2. So the idea of like tuples can be like 2-element tuple, 3-element tuple, 4-element tuple. Slice maps are the same thing. We're like, hey, I'm keyed by 1 value, 2 values, 3 values, 4 values, 5 values. This is like how many different, the dimensions of the data. So in this case, the first index is a string, the second index is a string, and the value is a float. And so now I can slice across 2 dimensions where I say like, hey, I want the values where the first dimension is A, but I want everything along the second dimension. Or I could say, hey, I want everything along the first dimension, but only the values where the second dimension is location 2, like this particular value. Or I can say, hey, the first dimension has to be greater than or equal to B, and the second dimension has to be less than location 2, right? It's basically just ways of like subsetting like an array. Same idea, but arrays can only be indexed by integers. This thing can be indexed by whatever, right? Which becomes really useful when you start applying domain modeling to your mathematical planning. Because now your dimension, like, hey, this isn't just a string, it's a location, which is like a single case discriminated union. Or I don't have time in the 4 hours to get like all the way deep into like the domain modeling, but let's just say it becomes very powerful as you go forward. Have I answered your question about slice maps, or is it still confusing?
No, it's clear now. Thanks.
Okay. But basically, think of it as like a map, except you can slice along different dimensions. That's basically the capability it's giving us. So if I come back to the coffee model and do a little bit of refactoring, I can make this a little bit cleaner. So the first thing is I'm going to put all this data. I'm going to do a couple things. I'm going to use a single case discriminated union instead of saying like, hey, this is just a string for modeling my locations. I'm going to wrap that in a single case discriminated union, which is an F# thing. So I'm basically putting more type information around it. And I'm putting the data into slice maps. So I can support both that, like the dot multiply syntax, and so that I can slice. And now all the same code that we saw before, but now let's do some refactoring. So instead of the warehouse cost expression being this whole thing here, now it is going to be the sum of warehouse cost. Wait. Where's warehouse cost? One moment. Oh. Something got remained. I have to refactor this as well. Changing these from maps to slice maps. And now I can just write the sum, warehouse cost, Hadamard product, warehouse decision. So it's doing the exact same thing that it was before. It's just a much smaller and cleaner syntax. Roasting cost expression is sum of roaster cost times roaster decisions. Same stuff before. This just becomes again, this is just making things just a lot easier to express. Same functionality, just a bit more terse. And these things will remain the same. Yep. And if I did this correctly, this should all work. Comment that out, uncomment this one, and I should get the same answer. Bring this over. Still built a roaster in St. John's, still built a roaster in Hawthorne, still had warehouses there as well. So same answer, just a little bit more succinct and easier to express. So that why we introduced that is going to make even more sense when we get to the next problem. So it has utility. Now, I think it's important we kind of ask the question, okay, Matthew, you've introduced the idea of like integer decision variables and Booleans. How do we solve this? Because that idea of like going from node to node that we talked about before, is that going to work anymore? Well, not really. You have to use a new technique. You have to add some tools to your solver. And again, for us as practitioners building models, we don't necessarily need to know these nitty-gritty details, but I think it's valuable to have some insight into how does a solver actually find solutions to these mathematical planning problems. And yes, sir.
What if there are two solutions of equal value, I guess? What if there are two solutions that meet the criteria that you specify? How do you find which one works, or how do you I guess view the two solutions that could potentially work?
Yeah, no, that's a fantastic question, and that's called having a degenerate solution. Was like multiple equally good answers, and that's very common to have. And there's a couple of different things you can do to deal with that situation. First of all, you have to ask yourself, do you care? I mean, if they're equally good, then great. But then you ask the question, well, are they actually equally good, or do I have some kind of preference? Right? We're just like, well, I would kind of prefer to have answers that went this way instead of that way. And that's where you could add to the objective saying like, hey, I can associate a small penalty with going with these kinds of answers, right? And so there's that. Depending on the library that you're using, it will expose different features for dealing with that and like viewing it. The way the solver works is it's able to detect like, hey, I've reached kind of an optimum. Like there's no way I can improve on this. And so it just like picks an answer for you, because from the solver standpoint, these are all equally good. So there's like, unless you give it additional information about things not being equally good, it's done. So it really depends on what your use case is and are they truly equally good or not? Because sometimes you can add a preference for saying like, well, let's say you had a model that you were solving again day after day after day after day, and the input was like the condition of the yesterday. And you're saying like, hey, I don't want you to like change a whole lot of things about this like 2-week plan that you're giving me. So you can associate a penalty with like changing answers. But again, that kind of goes into the specifics of your scenario and what you're doing. I don't have more content in this workshop about that, but I would be happy to follow up with you and have more discussions about that. And if you have a specific thing in mind, I would love to discuss that. So cool. So how do we solve these problems which have like these binary decision variables inside of it? So let's go back to like drawing a picture. In this case, x1 and x2 are binary decision variables. And let's say, sorry, they're integer decision variables. So only these points are actually valid solutions because it's where x1 and x2 are both integer values. And we add some constraints saying like, hey, these are the bounds of my problem. And this is the direction of the objective. I want to go as far in that direction as possible, right? So intuitively, if what we do, if we just solved what's called a relaxation, right? We're saying like, hey, don't worry about the fact that these are integer. Let's just assume they're continuous for now and like not sweat it. Solve that relaxation, that easier problem. And then once you solve, check the values. Is x1 integer? Is x2 integer? And if the answer is no, then we need to do something. So in this case, they're not. So we need to do something. Okay, well, what if we could add a constraint to the problem that eliminated that solution as a possible answer, but also didn't cut off any of the still good points, right? Which is what this new constraint just did, is that first solution it found, okay, that's no longer feasible. That's outside the bounds. But the blue dots where x1, x2 are integer, those are still legal. They're right there on the line, but they're still legal. So you might solve again and you find this new point. It's like, okay, well, now that you've added this constraint, I'm going to solve again, and I find this new point. Again, you check x1 and 2, x1 and x2. Are they integer? No. Okay, let's add a constraint to the problem to, again, eliminate that invalid solution, but keep all of our blue dots within the red lines. We add one, we solve again, and we say, hey, we check it. This looks good. That technique, sorry, I come back here. We kept adding constraints to kind of cut off these bad solutions until it actually landed on a point where x1 and x2 were both integer. That technique is called cutting planes. And the way it works is like, hey, we're going to solve this simple thing, and each time we're going to check, are we actually at integer values? Keep adding constraints as you need to until you land on one. Another technique would be, let's take that problem again, and let's create two sub-problems, right? And on one sub-problem, we're going to add a constraint saying x2 has to be less than or equal to 2. We're going to add that constraint. We've cut off a portion of it, and we solve again, and in this case, we land on a point. Sorry, the illustration's a little funky, but trust me, it landed on a point. And then on the right side, we're going to add a constraint saying x2 has to be greater than or equal to 3. But basically, because that original solution landed between 2 and 3 for x2, we're like creating two sub-problems where we're like branching and saying, hey, on the left side, I'm going to say you have to be over here. And on the right side, I'm going to say, hey, I'm going to add a constraint and say you have to be on the right. So now I add a constraint saying, hey, x2 has to be greater than or equal to 3. I've cut some space off. I solve again. Is that on a point or not? And you can imagine just kind of keep branching down and keep adding these constraints to these subproblems until you're forced to get to a solution where all your integer decisions are actually integer values. That technique is called branch and bound. You choose a decision variable, you branch on it, and then you create new subproblems with new constraints until you actually get to integer solutions. Now, as you can imagine, that's a bit more computationally intensive, right? Instead of just searching the nodes, which are where the constraints intersect. So what are key takeaways from that? Well, what we've been doing originally with continuous decision variables, that falls into the area of kind of linear programming, as some people have been alluding to in chat, which is fantastic. We can solve really big problems that just use continuous decision variables. And by really big, I mean over 100 million decisions and constraints. Really big. That might take a couple hours, but it'll solve. At that point, you're almost becoming memory bound. If you have integer decision variables, that difficulty goes up significantly. It's about 10x more difficult, right? So you can imagine the size of your problems kind of go down by 10x. And this is where I say, if you can, consider just modeling these decisions using continuous variables. So in the example of the cow, right? You can't raise part of a cow. Is it really like, can you still get a meaningful solution out? And one of the things that I think about is if my decision is like in the order of like tens of thousands, okay, is there a really big difference between 10,186.2 and 10,186? Not really. And so what's the impact of relaxing an integer decision to a continuous? Probably insignificant. I'm sure someone could come up with an example and like nail me, but probably insignificant. But if your decisions, if those values are on the order of like single digits, you probably need to stick to an integer decision variable because that's going to have a much larger impact percentage-wise. But if you can relax, please consider relaxing the problem using default to continuous decision variables if you can. When you start adding complex binary decisions and complex business logic, difficulty goes up into about another 10x, right? So you can still solve very large problems, but it might have to churn a little bit longer. So again, as a practitioner, you kind of like, okay, do I need to like reach all the way in right off the bat, or can I start with like a relaxation and kind of build up the complexity? Now, if a binary decision variable is the right thing for your problem, use it. Absolutely. And you're typically modeling logic at that point anyway. So it's probably the only correct thing to do. Just be aware of like the kind of like the magnitude and size of problems you can attack will really depend on the complexity of the constraints and the sheer number of decision variables, because the more constraints, that's more nodes, that's more intersects. So it's a larger tree for it to search. And the more decision variables, that's just the more knobs and dials it has available to adjust to kind of search. So just keep those things in mind. We are about to dive into another example that's kind of like the big one for the workshop, as far as like, hey, we're going to bring all this stuff together into a larger problem. But we are approaching the top of the hour again. So I think it's a great time for us to take a quick break. Example, we're kind of really bring everything together and kind of show all these features working together really smoothly. So this is what I call the power planning problem. And we need to come up with a plan for generating power to meet the requirements of a large number of cities. There's a fixed cost for turning on a power plant. So just turning the thing on, there's going to be a cost associated with it. They also have different generation efficiencies. So for every dollar, you get a different number of kilowatts depending on which power plants you're using. Cities have different power requirements, so they're min kilowatts. So we have a set of cities. We have a set of power plants. We have the power required for each city, the max power generation, so how much power can a given power plant put out, the startup cost for that plant, and the power cost. So our decisions are going to be, do we run the power plant or not? Do we turn it on? how much power do we generate at a plant? How much power do we send from a given plant to a given city? And different cities have, not every power plant is connected to every city. Our objective is a minimum cost plan, and that's going to be the sum of turning on power plants plus the sum of the power generation cost. Our constraints are the power capacity. For each power plant, the power must, well, capacity and startup required. The power plant must be turned on if it's generating power. We also have a power balance. For each power plant, the sum of the power that it sends has to be equal to the power it actually generates. You can't send power you didn't generate. For each city, the sum of the power it receives has to be equal to the power required. So you actually have to send how much the city needs. Let's jump to the code. Go ahead and comment this one out. Uncomment this one. And we're going to jump to power planning. Now, again, I'm using some F# stuff. So these are single case discriminated unions. And basically, this is a very simple way of creating a type. And I'm wrapping these strings in some type information, essentially. Where I'm saying, hey, before we were modeling things using just like a raw string, but because I'm indexing across multiple dimensions now, because I have the power plant and I have the city, I want to provide some more domain-specific information. So I am indexing, I'm creating a list of cities. This is a city list. And I've created that type here. So this isn't just a C1, this isn't just city one. I'm wrapping it in a type. So now it knows like, oh, this isn't just a string, it's a particular type. Same with power plants. I have the string, which is the value, but then I'm wrapping it in that discriminated union case to say, hey, this isn't a list of strings, it's a list of plants. And then I have my connections. So these like city one is connected to plant 1, city 1 is connected to plant 3, and city 1 is connected to plant 5, right? This looks a little clunky all written out, but can you imagine this? You would be getting this from like an ERP or a database or some other user management thing. I have the max power generation limits for the power plants. I have the startup cost associated with each power plant, the power cost, startup, okay, max power, startup cost, power cost for a power plant. So how much does it cost per kilowatt it generates? And then the power required for each of the cities. So let's get to it. So I need some decisions for whether to run the power plant or not. So let run power plant equal to decision builder run plant for plant in power plants Boolean. And now, so what this is saying is like, hey, 0, don't run the power plant. 1, run the power plant. And I'm going to put that into a slice map where the key is the plant and the value associated with it is the decision. And now I need to create decisions for how much power they generate. So let power generation equal decision builder power generation. For plant in power plants, I want to create a continuous one from 0 to infinity. So this is basically the knob, the dial on the power plant, like, hey, how much power are you going to generate? We will create constraints which limit that, but right now we're just saying, hey, the bounds on this are 0 and infinity. And then we need to create decisions for saying how much power do we send from a given power plant to a city. Let power sent decision builder power sent for connection in connections, because you remember it's sparse. Like not every power plant is connected to every city. Again, I have continuous from 0 to infinity. So this is going to say how much do I send along the power lines from a given power plant to a given city. So I got 3 different kind of sets of decision rails. And here I forgot to put this one into a slice map. So you see run power plant, slice map, index by plant, the value is a decision. Power generation, again, slice map, the key is a plant, the value is a decision. Power sent, connections is a list of city plant tuples. So connection is a city plant tuple. I'm putting this into a slice map 2. Why does that matter? The first dimension is the city. The second dimension is the power plant. The value is the decision. So basically I'm indexing it by 2 different dimensions. So you can imagine like this, it feels like a 2D array. One dimension of the array was the city, another dimension was the power plant. But I'm using domain types to more accurately describe my problem space. Instead of just using ints as indexes, we actually have types. It is very easy to screw up indexing with these problems. So startup cost expression equal to the sum of startup cost times run power plant. What is the cost for each plant multiplied by the decision of whether to run that plant or not? Sum the whole thing up. Instead of having to write out like a list expression and doing all the indexing, it just takes care of it for us. We also have the power cost. Power generation times power cost. Power generation are the decisions about like, hey, for a given plant, how much do I turn the dial? And this says, this is how much it costs for however much you turn the dial. Let total cost expression equal startup cost expression plus power cost expression. And let objective equal objective create minimize cost minimize total cost. Are we still following? Cool. I will take the silence as a yes. Very encouraging. Good times, good times. We need to add some power capacity constraints. So now we're going to start using these constraint builders a little bit more heavily. So power capacity constraints equal constraint builder power capacity. And this is going to be for plant in power plants. I want to create a constraint. So this is where slicing becomes really important. So power generate, well, not quite, never mind. Getting close. So power generation for a given plant has to be less than or equal to max power generation for that plant times run power plant. Okay, why did I write this? I have a decision which says, do I use the power plant or not? Now, naturally, the solver doesn't want to use it because it costs money to turn on a power plant. So I have to have a constraint which says, like, if you're using it, you got to turn it on. The amount of power you generate has to be less than or equal to the max power generation times whether you turned it on or not. If you didn't turn the power plant on, 0 times anything is 0. So the amount of power you can generate has to be less than or equal to whatever this is. If you didn't turn the power plant on, this is 0. You can't generate any power at that power plant. If you turn the power plant on, this becomes a 1. 1 times the max power generation is the max power generation. You can turn this dial up until you hit this value. That's what those constraints are doing. You got to turn the power plant on. Once you can turn the power generation up as high as you want until you hit that max power generation. Now we have our power balance constraints. So if we're like, hey, however much we generate and however much we send, this needs to make sense. So let power balance constraints equal constraint builder power balance for plant in plants, the sum of power sent. Okay. Correct that mistake right there. Power sent. Okay. This is where slicing comes in. Power sent. 2-dimensional slice map, where the first index is a city and the second one is the plant. I want to sum up all the power being sent by a plant to any given city. So first dimension is city. I want all the cities, but I only care about this particular plant right here. That has to be equal to the power generation for a given plant. Does this make sense what happened here? I'm basically saying, hey, power sent, 2-dimensional thing. First index is city, second index is plant. I want all the cities, but I'm only looking at a particular plant at this moment because I'm going to loop through each of the plants. For each power plant, I'm going to create one of these constraints. Now we have the cities powered constraints. For city in cities, sum power sent. First dimension is cities. I'm looking at a particular city at this moment. I want all the power sent to that particular city from all the power plants equal to the power required for that city. So I'm going to create a constraint for every single city in my problem. And that constraint is, hey, that city, the sum of the power I send to it from any given power plant has to equal the amount of power that the city needs. So there's a question in the chat I'd like to address. Why do we need extra decision for turning plant on or off, as opposed to just deducing it from whether the power generation is non-zero? Is it perhaps because the cost expression has to be linear? You need that variable to account for the startup cost of the power plant. You need something that gets turned on to turn on that cost, essentially. So if you just used, so that's like the simplified version of it, because if you use like, hey, how much power I'm generating, you can't multiply that by the startup cost, because like the more power you generate, it's only like a small amount of like the startup cost. It basically has to do with like modeling startup cost. It's a cost you pay once when you turn the power plant on, and you don't have to pay it again. You need to model that type of thing using a Boolean or binary decision variable. It's like you pay it or you don't. The follow-up question was, so the cost expression can't be an if then else expression. And I think this kind of goes back to the discussion we were having in the last break, which is a really good one. So the answer is no, not right now, because that's not how you model the cost expression. It has, like, you're basically limited to these tools: continuous decision variables, integer decision variables, or Boolean. Now, in the future, we can make an enhancement, which makes it easier to express that. And if people have opinions on what that should look like, I would love to hear it, right? And if you could easily go to the Flips library repo and like put in a suggestion or a comment there and say like, hey, I have a real world scenario. I would like to be able to say this. Great. We would love to take that. And hey, if you want to help, we welcome it, because those are the kind of things that we want to identify to make it easier for people. So now we need to bring this all together. Let model.create objective model add constraints, power capacity constraints, model add constraints, the power balance constraints, model add constraints, cities powered constraints. Same default settings. Let result equal solver solve settings model. And we will see what we get. I think I already commented this out. Yep, good to go. See what happens. So it's saying, hey, I want you to run power plant 1, power plant 3, and power plant 6. And then if we really wanted to, we can go through, and what we see up here, like how much are they generating? It's generating 35 kilowatts from power plant 1, 223 for power plant 3, and 165 for power plant 6, and it's not generating power at 2, 4, and 5. The key thing here is that, like, hey, for the plants that it's actually generating power at, it's also remembering to turn them on, and that is going to be reflected in the objective as well. So we can see, if we wanted to, which we're not going to right now, like look through and like, hey, are we meeting all like the power requirements for all the different cities? Like, how are we sending it? Those are being met. And you can imagine that this type of model can get much more sophisticated with more power plants, more zones, more cities. This is the kind of thing that's happening all day, every day, as people are optimizing the power generation plans for countries and regions, is because there's limitations on how much power you can send along different power lines, how much you can generate, and you got to find this best network distribution while meeting the requirements of the different cities. Any questions on all of that? That example kind of threw a lot at us. Okay. So, key takeaway from all this and this kind of introduction to mathematical planning: if you have a problem where you have decisions that need to be made, constraints that need to be obeyed, and a quantifiable objective, you have a mathematical planning problem. And very well may be that this would be a great tool for what you're doing. I've seen these types of problems crop up in all kinds of places that I would not have suspected before. So that is the end of this portion of the workshop. And we're actually going very quickly. So we're going to get done well before time. So we'll have tons of time for Q&A. You guys aren't asking as many questions, which is great. So I'm either doing a great job or I'm just like so bad. You don't even know what questions to ask. So we'll keep trucking along here and get the next thing. Let's talk about structure and testing. Like we've gone through a bunch of examples of how to do mathematical planning and like how to model and how to decompose things into mathematical planning problems. Okay, that's great and cute and all. What about the challenges of putting things into production? Because that looks a little bit different. These have been cute little scripts in here. If I want to put something into prod, that's going to be a little bit more difficult, right? So kind of key points I want to hit in this next section is like project structure. How do we structure our models and structure our projects to make it easier to maintain these models going forward? The last thing we want to do is what we don't want to do is throw together a bunch of code into this like giant function and say, hey, I've done the thing and it's completely untestable, right? There are things that we can do to make it more testable. And that kind of goes into how we structure our code. And then we're going to talk about testing methodology and how do we test these things? Classically, they're not. A lot of people working in this domain don't have unit tests, which is terrifying. As a software developer, well, someone who's become a software developer, this is the world I came from. So I used to be that person. Now I hang my head in shame. So don't judge me for my old code. My code has tests now. Don't worry. So to do that, what I'm going to do is I put together kind of a really simple project. And if you go to the repo, and if you want to follow along or look at this later, what you can do is you can go to code and go to the coffee planning example, and you just go ahead and open up the solution. And this is a really, I took the coffee planning problem that we did earlier, and then I said like, hey, if I was to actually put that in production, how would I structure that? How would I do that? And what we have is the model code here in its own project where we have domain, model, and solve. And then we have a test project and some CLIs and consoles. And so we're going to talk through this a little bit to see like, hey, how is this put together? So one of the things that I recommend, and you do you, is separate configuration types from like the domain, which is your problem. Create a little miniature domain for your mathematical modeling problem, which makes it very easy to express a problem in that. And then have a separate set of types which are used to like feed in the configuration information and write a function that maps to it. You will save yourself a lot of grief if you do that. Is there a question out there? Here's someone off the mic. Cool. Feel free to jump in, whatever. So what I'm doing here is, again, just go back to the coffee planning problem that we did earlier. Exact same thing. We're defined a configuration type. It's got a location, which is just an array of strings, some warehouse costs, which are just dictionaries, and min warehouse capacity, min roaster capacity. Very simple stuff. And then I recommend defining a return type, or like, this is the thing I'm going to give you back. Right, so a plan. And what it is like, hey, I'm going to give you an array of the warehouses I selected, an array of the roasters I selected, and what the total cost for that plan was. And basically that is like the entirety of the external facing API, right? It's just like, these are the different types. Everything inside of this is my own little world that is for mathematical planning. So then I start defining the types for the model itself and what it's going to use, and which is why I put internal on here, like no one else gets to use this, where I say, hey, I'm going to start accurately modeling my domain using some single case discriminated unions, in this case, using location. Parameters is the internal type that the model likes to use, which if you notice, like, hey, this is now a list of locations, slice map of location and float. This is what this is how the model code likes to work. And the reason I stress this is because if you're doing this in F#, if you're like, hey, Matthew, I'm never going to use F#, don't worry about it. Okay, this isn't for you. But in F#, it's very nice to work with types that are very F# idiomatic. But not all other .NET languages really play nicely with those types. And so what I expose externally is like really basic stuff that every .NET language will be very happy talking to. And then internally, everything gets F#y and written in that way. And so parameters is what the model code is going to take. And then I just find just a really simple function for saying like, hey, I take a config, which is this external facing type here, and I'm going to turn that into the parameters. And this is where I'm mapping from the external to the internal domain. So typically a domain file where I'm kind of modeling my solution space. And then instead of having a monolithic function for building the model, just like in one pass, I separate it out into the different components. And why do that? Great question. And it comes to testing. So I'm going to kind of like walk through this, and then we'll get to why it really matters so much. So in here, go ahead and minimize. I have a function which kind of creates the base model. So it takes some parameters and my decisions, and all it's doing is say, hey, here's the cost expression, here's the objective, model.create, and this thing returns a model. So all it's doing is creating that initial model that, with the objective, and then you're going to add constraints onto it. And then with very long names, very descriptive names, I say admin warehouse capacity constraint. And so it takes parameters, the warehouse decisions, the model, and then it builds those constraints and adds it to the model and returns the model. And so each one of these, like, hey, admin warehouse capacity, admin roster capacity, add warehouse required constraints. So each of these functions is just doing one thing to the model, where it's like, hey, I'm adding these kinds of constraints. Why do that? A couple of reasons. I mentioned testing, and we'll get to that. But the other is, like, it makes it very easy for someone to come in and say, like, where do we add the constraints that do X? So instead of having to scan through some model code that's like super long, it's like, no, just go to the function that does that. And it's very easy to identify and maintain that code. And then I have a function which is build model, which is like, hey, it creates base, and then it adds those constraints, and then it adds them in warehouse constraints, and it does that. So like this is kind of like the compositional root, I think is the term, but basically this is the thing that kind of like puts it all together, but they're all defined as separate functions. And then what gets exposed externally, go ahead and minimize these, is basically the find plan function. This takes the config, which is that external facing type. It takes a max duration, which is like, hey, how many milliseconds do you want me to churn on this? And then it does the work and does the solve. And so as far as like what gets exposed, it's the config type, it's the return type, and it's this find plan function. That's it. Everything else is internal to the library, and so it's not exposing any of that other functionality unnecessarily. So that'll typically be one project. Then we want to add tests to it. So in this case, we typically like to do property-based testing, but I don't have enough time to kind of get into property-based testing. So we're just going to show some unit tests. And here I have tests. And in this case, it's the same data that was in that problem. So same thing that we saw before, except now let's talk about the different tests. I have 4 different tests here. How does this work? I really like the idea of the arrange, act, assert kind of paradigm for writing unit tests. So nice long name saying like, hey, base model selects no locations, right? Because if the model formulation is correct, it's trying to minimize its costs. It's not going to do anything. So let's think about what's going on here. Creating the base model and then adding the different constraints, they're all separate functions. And so I want to test that if I create just the base model, no constraints, I want to verify that it doesn't actually select anything, because that would be the minimum cost plan. Now remember, there's no constraints at this point. So model, create the base. I'm going to give you some parameters, and give you some decisions, and I want you to solve it. And then I'm going to assert that, hey, you didn't choose anything. Because right now, I haven't given you any constraints like, hey, you have to do these things. I just want to verify that that logic is working correctly. Then what I can do is like, hey, now that I verified that that works correctly, I'm going to add one layer of logic to this now. And I'm going to test that small piece of additional logic I added to the model. And in this case, I'm going to take that base model again, which has the objective, minimize my costs, but I'm going to add one set of constraints to it. In this case, it's only one constraint. You can imagine it being more, but add min warehouse capacity constraint. And say, hey, solve that. And then what I do down here is they say, hey, of this, like that plan that you gave me, did you select enough warehouse capacity? So I'm just verifying that these warehouse constraints are acting correctly. So by separating these functions for adding constraints to the model into separate functions, we're able to verify them independently instead of having to like make these really complex tests that take everything into account. Trust me, these are all very simple models, but if you have larger, more complex ones, trying to test all the different scenarios gets really difficult if it's all the constraints at once. So it's really nice to just take subsets of the constraints and verify that those are behaving, because the addition of all those constraints together should still be valid. And then have the min roasting capacity test, where I take the base model, but instead of adding the warehouse capacity constraint, I'm just adding the min roasting capacity constraint. And then I'm verifying that, hey, the sum of that, did you give me enough roasting capacity? Then I want to say, hey, are you building a warehouse wherever you build a roaster? Now, this one's a little different. And the order of these tests is significant, because the first thing I tested, like, yes, create the base model works as intended. I've tested add min roaster capacity constraint. It does what I expect it to do. That was a test farther up. And now I'm adding add warehouse required constraints. So now I'm adding 2 sets of constraints to this test. Why am I doing that? If I don't have this in here, and I say, hey, I want to add warehouse required constraints, a valid plan would be don't build anything. So I'm not actually testing the constraint at this point because there's nothing that's actually like pushing against that boundary. There's not anything forcing it to do anything. So I need to add a constraint, which is going to force it to build something. For this constraint, add warehouse required constraint, to actually like do something meaningful. But I feel comfortable doing that because I already validated the behavior of this constraint in a previous unit test. And so it's this idea of like, I can layer on the number of things that I'm testing. So I'm testing in isolation as much as possible, but there may be a time where like, no, I need several layers of constraints to like really push this new constraint that I'm testing. So that's why I really encourage people, don't write monolithic model code when you're going to production. Totally fine to do that during exploration, these kind of fun examples that we're doing here. But when you're saying like, hey, I'm going to take it to prod, I'm going to have unit tests and maintainability, I strongly encourage separating those out into different functions. It may seem a little over the top, but you'll be so grateful for tests and the maintaining of the tests if you follow that paradigm. And so, in theory, if I did this correctly, I should be able to run these tests and nothing will blow up in my face. But no plan survives first encounter with the debugger. Oh, look, it passed. Good. This is why I didn't break any of my code. So you can see like, hey, these are all working as intended. And it's very easy to identify which thing is testing which piece of logic. Any questions about this and testing and model code structure?
Yeah, can you test a constraint even in more isolation than you have now? For example, forget the property-based testing for a moment, even though I also like it.
Mm-hmm.
What if you provide values to the constraint, and or with a constraint and some values for the variables involved, and then some piece of code, some other function can tell you like whether or not the constraint is satisfied with those values? The reason I thought of that is, right, the goal of testing is to be less complex than the production code.
Mm-hmm.
That's the sense in which we're not forming a circle of like, how do you test the test code?
Mm-hmm.
The point is that the test code is simpler than the production code. I don't know what the right level of complexity is, but it would definitely be simpler to give specific values for like these roasters and warehouses and be like, this does, and say that these settings should satisfy the constraint and these other values should not satisfy the constraint.
Yeah, no, that's a really great point. I'm gonna take another note.
Especially if we just have like 2 Boolean variables, this is where it's like legitimately reasonable just to express all.
Yeah. So is there a really straightforward way of doing it right now? No. Can you do it? Yes. It's a little clunky and could be made a lot cleaner, which is why I took a note. I'm like, oh, well, we could actually make that really easy. But you just need to add a function to the library, which is like constraint, just like verify or something like that.
Mm-hmm.
Because what you can do is you can basically pass in a solution. So solutions in this case are like, hey, for these decision variables, I chose these values. You could pass it in and say like, hey, using this solution, wink, wink, nudge, nudge, verify this constraint. And if like, actually, no, this just broke. That would be a way of testing like individual constraints. Now I really like that idea and would take this to like another level of granularity. No, that's a good one. So
if I had to guess, I would think that some of the solvers use some amount of randomness. So in that like strict sense, they're not unit tests either, but I'm not like trying to be too picky about that.
Yeah,
But
no, that's
like you're pointing out, you provide the solution as part of the test so that you don't need to use the solver as well.
yeah, completely fair. So yeah, is it strictly a unit test? Yeah, probably not. It's probably more of an integration test.
Yeah.
At that point, that's
But
fair.
to be fair, property-based tests are already using somewhat around this anyway, but in a very controlled way, I would say.
Mhm. Yeah.
In a way that's understood by the testing approach.
Yep, agreed. No, great points. I'm really glad you brought that up. These are great things that we can add. This is what we've been getting away with. Any other kind of thoughts, questions on this portion? This is a really easy audience. We're going to end super early, so it's all good. I think part of it has to do with the community that this got sent out to. Well, cool. I'm going to keep going. Those are the main things I wanted to cover there. And here I just kind of provide like a silly example of like, yes, you can use the F# stuff from C# and everything is fine and happy, right? So this is just, hey, there's a config file, which in this case is just a silly old JSON with the data in it. And then just using Newtonsoft to bring in that information. And this is like, hey, I'm just calling the F# code and everything just plays nice and works as intended. And I'll go ahead and run that and bring this over. We're saying like, hey, I selected these warehouses. I selected these roasters, and this is what the cost is. Very easy and straightforward. And so this is one of the scenarios that we also deal with where a lot of the code at our work is in C#. A lot more C# developers out there in the world than F# developers. But that doesn't necessarily mean that, oh, we just need to do it in C#. Like, well, they play perfectly nicely together. And none of the F-sharpy weirdness kind of leaks outside of the library because of the types that we declared here inside the domain. It's like these are very purposely chosen to play nicely with any .NET language. We are coming toward the top of the hour. So I think what I'm going to go ahead and do is call our last break. Okay, we're in our last stretch here. So we're going to end here pretty early, which is great and give you some time back. But I'm also happy to stay on, answer people's questions, just have a conversation. I really appreciate everyone taking the time to be a part of this. So thank you so much. Let's talk about deployment scenarios. And this one is not terribly exciting, but I think it's something to kind of some things to keep in mind as you're going to move something to production. Saying like, hey, I want to put this into production. Well, there's really different use cases for models. And I kind of think of it as on a spectrum of strategic to tactical, right? Strategic models versus tactical models. And it really has to do with like, where are they adding value? Where are they used? Am I using a model to investigate something way out in the future and consider some plan for the next month, 2 months, 3 months, a year? Or is it something where I'm needing to make a decision right now? Like tactical is something, the decision to be made this moment, this hour, this day. And models, these mathematical planning models can be used in both scenarios, but depending on the scenario, that's going to affect which deployment method you decide to use. And again, this is mostly just software engineering best principles. So there's not going to be a whole lot new. When it comes to strategic models, these are typically models where the purpose is exploration. You see this a lot with capital investments, like, hey, we're going to build some buildings. We're going to locate some warehouses. We're going to make some investments. And we want to find what the best possible plan is for locating warehouses and distribution. as an example. And that's going to be a long-term plan. You can put in the costs, you can put in the demands, you can put in expected growth, and the mathematical planning model will tell you like, well, this is the best one. But then what you can do is you can play with it. You can adjust costs and see what's it sensitive to. Like, hey, if like demand changes this much, there's actually a better plan. And so we're going to analyze projects and look at things well into the future. The user is going to want to adjust those inputs and explore if my capacity requirements double, what would the plan be in that case? And like, hey, is this a significantly different plan? I want to know if I'm taking on some undue risk, if like these inputs change significantly. And they'll want to compare results with what other solutions were. And really the value from strategic models is in the exploration. I'm allowing the user to change values, change knobs, change dials, and see what the different solutions are. And like I said, it becomes very useful to have that understanding because like, okay, if things go according to plan, and after this last year, we all know how often that happens, this is the best plan. But what happens if we have like a 50% reduction in capacity, or there's a 10% reduction in our budget or something like that? What would the best plan be in that case? So it's really useful for being able to explore what is my solution sensitive to, like what things really matter. And so you can kind of go into the future with kind of your eyes wide open as far as these are the things I really need to pay attention going forward. These are the things I need to pay attention to going forward, because if these factors change significantly, the best plan changes. And so it's an early warning tool versus tactical models where I need a solution today. And a tactical model is more about, I need a prescription. I want to know what to do right now, like today. And so it's not so much, I want to, like if you're working for UPS and you're delivering things, you want the best possible plan for delivering packages. There's no exploration going on. Like I need a plan so I can execute on it. That's it. The model is typically focused on near-term things, either today or this week. And so it's like, I need to take action on this, and it's immediate action. The solution is typically not iterated on. You're not saying like, well, I don't like that solution, give me a new one. Oh, I want to adjust some of the parameters, give me a new solution. Like, no, it's like, this is what you're going to do. This is what you do right now. And comparison to previous solutions is not really a requirement in this scenario. I want a prescription. I'm going to execute the prescription. This is used a lot of the time when you have like a manufacturing floor and you're needing to sequence things and find the best plan. In real time, you can send in location data, say like, hey, this is the best plan, execute this. There's also situations where like, hey, we need to manage loans, right? And there's different ways that we can finance loans and move loans around, and there's time requirements around that happening. And so we can't take a long time for someone to figure out how to allocate 10,000 loans. Like, we need an answer right now. The money needs to move. So having a mathematical planning model that finds the most profitable way to slot loans would be really useful, right? And so it's the fact that it's time bound, it's tactical, it's a decision, it's something I'm executing on right now. And so I always like to think about models and where they lie on the spectrum between the strategic and the tactical. The value is providing that immediate answer. For those of you who want this all on one slide, there it is, with a comparison side by side. So this is the first thing that I always suggest someone thinks about when they say, hey, we've got this cool model we want to put in production, or we want to develop a model, right? Think about the type of model that it is. And then we start discussing types of deployments. How are you going to get the model into the user's hands? So kind of the silly, simple one that I like to start with is just pick a command line tool. Like is like amazingly simple. And if you have expert users, sometimes this is all that they need. Where it's like, hey, just give them a command line tool. They'll point it at some input. It'll spit some data out, and then it'll spit like a CSV out or something like that, and then they can analyze it to their heart's content. Really depends on your users, obviously, but the amount of additional value you can get from a mathematical planning model can be really significant. So if you can get it into the user's hands faster by making a really simple tool and then verifying it's behaving the way they want, I strongly suggest that. And it always blows me away every time I sit down with the business, some partner or someone I could develop a model for, and we get this great discussion about, oh, I need the model that does this and does that. And these are the constraints, da, da, da. And I get to the end, I'm like, well, is that everything? Oh, yeah. That's everything. We build the model. We deliver the model. Oh, right. But it needs to do this in this situation. Like, oh my gosh, you gotta be kidding. It's inevitable. Like, and it's always funny. They'll inevitably forget something. There's some additional business strategy thing that they forgot to voice. And so by getting it to market, quote unquote, getting it to market quickly, you're getting feedback on that much faster. And what's also interesting is a solver is not a human being, which sounds really obvious, but we have so much context around our business domains that we don't even consider some decisions. Like we wouldn't even like, for example, like if you don't put some kind of constraint in for something, it could say like, yeah, you should totally build the warehouse on top of Mount Everest because it's got the best distribution between these different regions. Like you would never build on Everest. Why would you do that? The solver doesn't know. It doesn't have that context. So the solver is going to do the best it can to maximize or minimize that objective. And sometimes it might do something that may seem silly because the constraints allow it. And what ends up happening is that prompts a really valuable discussion with the business around, well, you say you don't do this right now. Maybe you should, right? Maybe the solver is exposing a strategy or some idea that you never considered just because you're a human being and like you don't think about all the different edge cases. Maybe this is something that you should do. So that is exactly what has happened to us when it comes to loans and financing loans, is that there's a strategy that the business was taking just because that's what they got used to. And then we put together a solver and we said, hey, check out what this is recommending. They're like, we never considered that. Yes, that is technically allowed. Interesting. And so the solver is going to do that. And so the sooner that the users, the business, the client, whoever is seeing the results and providing feedback, the better. Which is why I say, like, start with the stupid command line tool, get some feedback on it, because inevitably you're going to get more feedback. There's also like the classic, like, hey, just expose something in Excel. And I don't know about your industry, but Excel is basically the operating system of finance. Everybody uses Excel for everything. And so if you can kind of marry the command line tool with like, hey, it takes an Excel in, does its optimization and spits the results back out in an Excel, it's amazing how many business users are super happy with that solution. And again, it's pretty quick to develop that. Do I like it? Depends. If your model is actually in source control and tested, you're already miles ahead of a lot of people. Then you can kind of upgrade, like, hey, we're going to host this as a web service, and we're going to put it in some like Docker container somewhere. We're going to expose some web API. Yeah, this is a lot of what we do. There's some nice things about it in that you can make sure everyone's using the same model, right? Because you're actually in control of the back end that's actually running the model, instead of everyone kind of having possibly different versions of the code on their machine. But you're taking on more of a maintenance burden because there's more things in play. Again, there's nothing shockingly new here. This is just kind of software engineering best practices. And then there's the option that I always strongly recommend against, which is some kind of ERP integration, something more tightly built into whatever service that they're using. I have often found that it's so much easier to get a data dump, feed that data into the model, have it produce a data dump, and then have someone load it back in. I actually haven't worked with a ton of ERP, so I don't know all the complexity here. I just know that at one gig, they were using SAP, and I just remember it just being insane to try to get stuff in and out. So it really kind of depends on your business and your use case. It's just like the sooner you get it into the user's hands, the sooner they're looking at the results and verifying whether those results make sense, the better. So I strongly encourage like starting with something super simple and getting in their hands, because so much of the value from going through this exercise is exposing biases and presuppositions that people have that are not valid. And what I have found is by sitting down in a room with people and saying, okay, what is the objective? What are you actually trying to achieve? If you have 10 people in that room, you'll have 10 different answers. And even if everyone's using the same words, oh, we're trying to maximize revenue. Well, different people are measuring revenue in different ways. And so by forcing people to have this discussion, forcing people to actually codify these things, it actually brings a lot of unity to the team in that everyone is working out the same definition of the truth. And the model ends up being kind of the codified business logic. And everyone agrees like, oh yeah, this is what it is, what we're actually trying to do. That is a super valuable discussion to have. And one of the reasons that a lot of times you get a lot of value from going through this even before you've developed any model code, because you force people to actually get on the same page. What are the constraints? What's actually a constraint? What's a preference? Oh, we prefer to do this. Okay, but are you actually, do you have to do that? Well, no. Okay, then we're not going to put it in as a constraint. And we're going to see what the model does. And that is exactly what was happening with our loan trading, is people had some presuppositions. They didn't even consider some possibilities. Turns out those were some good possibilities. You shouldn't have disregarded them. So great to go through this. So that's all the content I had for this. You were an amazing audience, and I really appreciate you taking the time. Feel free to reach out to me anywhere with questions. Email is by far going to be the most reliable way of getting a hold of me really quickly. I'm also on Twitter. I'm on the F# Slack, and we also have the GitHub. And yeah, if you have any thoughts or suggestions, I'm really happy to hear them. Like I said, I really appreciate you taking the time. This has been really fantastic. And I'm planning on kind of staying on and just kind of fielding people's questions and whatever. This was recorded. I'm going to edit out the Q&A portions, and so it's just going to be the presentation. And once I get that up, I will send out an email to everyone with a link to saying like, hey, the video's up. I'm also going to send out a follow-up questionnaire, just kind of getting people's feedback, because every time we've done this, we've gotten really valuable feedback. It's really shaped the direction of this workshop. So expect that in the next couple of days. And it'll be really quick, but it provides me a lot of value because it helps me make this content better and more applicable for people. So thank you all so much. I hope you guys have a wonderful day. Thank you.